So now that we've looked at weak acids, it's now time to turn our attention to weak bases. And as we've said earlier, bases are substances that can gain a hydrogen ion. So we have two types of bases. We have one that's like a molecule, and we wrote this kind of weird NR3, but you can think of this as like, for example, something like NH3. So we'll just do NH3 for a moment. And then when it reacts with water, it's going to gain the hydrogen to become this compound, NH4 positive. That's just another way of writing it, plus the hydroxide ion. So that's one way it can take place. Or it could be an anion, such as X negative. So we could do something like, say NO2 negative. And as it gains a hydrogen from water, it would become HNO2. Okay, so that's two different kind of bases that you can see. Notice that in the second example, this has to be the conjugate base of a weak acid in order for this to exist as an equilibrium. So you can do this with, like, say, Br minus or I negative, which are conjugate bases of strong acid. Okay, so the calculations that we do for the pH of a base is very similar to what we were doing with the acid for weak acid. So when you look at this problem, this is when it becomes really, really important to show the hydrolysis equation and to make sure you include water with this one. So methylamine, I'll just make this one, I'm going to call this B negative to represent a base. And as it undergoes hydrolysis with water, we want to make sure this is aqueous, and then this is the liquid. And it's going to undergo equilibrium, and it's going to gain a hydrogen, and also create hydroxide ions. And bases produce hydroxide ions in water. So the equilibrium expression is Kb equals Hb OH minus over the conjugate base, the conjugate base would be negative. And the initial change equilibrium, initial concentration is 1 molar. We're going to X out the water column, and these are both 0. Okay, so we're going to find the pH first by finding the pOH. And in order to find the pOH, you need the OH minus concentration. So we're going to put X for OH minus at equilibrium, and then plus X, minus X. And then this is 1 minus X, and this is X. And we're going to assume, for now, with the track ionization, that this is negligible, so that this is approximately equal to 1. Okay, then we're going to plug this into the Kb expression. 4.38 times 10 to the negative 4 equals x squared over 1. And we're going to go ahead and run that calculation in here. Say that's the square root of 4.38 times 10 to the negative 4. And that would give you x is approximately 0.0209, and we're going to do the ionization check. 0209 divided by the initial concentration of 1 times 100 is, say, 2.09%. And that's less than 5%, so we can verify that the X is negligible on the initial concentration. Okay, so that X is same thing as the OH minus concentration. And we can use that to find the pOH by taking the negative log of that number. The negative log of 0.0209 to give you 1.68. And the pH of that, we're going to subtract that from 14 to say 12.32. So you can see it's very similar to the way that we calculate the pH of a weak acid, but you just need to make sure that you're aware that we're dealing with the Kb expression, okay, and the Kb value, which is talking about the equilibrium involving the hydrolysis of a weak base. Okay, so take a moment to read this problem and see if you can guess, take a good educated guess as to what the correct answer. So pause the video and read the question. So hopefully you at least eliminated the last one, nitrous acid, because that's an acid and that has a Ka value, which is going to be greater than a Kb value since it's more likely to act as an acid. Okay, so between the other two, we want to look for one that is going to be more basic, because a higher pH means that it's going to be more basic or stronger. So you want one that's a stronger base. Okay, and that would mean they have loss and loss of OH negative, and that would be more, or not loss of, but relatively more OH minus. So you want something with a higher Kb value. So in the case of this one, it will be methylamine. Now be very careful, because if I ask for the lowest pH, you're going to be looking for something that is more acidic, a stronger acid. So you're going to look for a higher Ka value when you're looking for a lower pH. And students oftentimes get that mixed up, that a lower pH is associated with a greater concentration of H3O plus ion. Okay, so now let's talk a little bit more about Ka and Kb. And you want to make sure that you understand that the relationship between Ka and Kb right here, that equals 1 times 10 to the negative 14, but that's only for a conjugate acid-base pair. So, for example, the Ka of HNO2 times the Kb of NO2 negative would multiply to 1 times 10 to the negative 14, which is the same thing as Kw, the ionization constant for water. Okay. We spoke earlier about what it means to have a P in front. The P means just take the negative log of that. And you can go backwards by find the Ka by going 10 to the negative pKa power to find out what the Ka value is. Okay, and you don't have to know this, but you might find it useful to know that Ka, pKa plus pKb equals 14. Okay, and once again, that also refers to the conjugate acid-base pair. Okay, so this question asks you for the Ka for NH4 positive. So the way you can go about doing this is to look up the Kb for its conjugate base. So noting that this is the acid, the conjugate base equals NH3. So we're going to look up the Kb for NH3, and that is 1.8 times 10 to the negative 5. Okay. So then, to find the Ka for the acid, you know that Ka times Kb equals 1 times 10 to the 14th power. So if I divide 1 times 10 to the negative 14th by 1.8 times 10 to the negative 5, okay, I should get 5.56, I'll just say 5.6 times 10 to the negative 10. Okay. And again, I want you to note the fact that this value of Kb, 1.8 times 10 to the negative 5, indicates a weak base, and then a conjugate acid, Ka, is also less than 1, 5.6 times 10 to the negative 10. And that also in the case of weak acid. So remember that a weak acid has a weak conjugate base and vice versa. A strong acid has an extremely weak conjugate base to the point that it's negligible. Okay, but this is the mathematical evidence here that a weak acid and a weak base conjugate exist like that. Okay, and Kb for the acetate ion. Okay, so that would be the acetate ion. Remember your ions here would be CH3CO2 negative. Okay, so we need to look up what the Ka for acetic acid is, because that's the conjugate acid. And it so happens that it's going to be the same as the last problem, just a coincidence, 1.8 times 10 to the negative 5. So the Kb for the acetate ion would be, once again, 1 times 10 to the negative 14 divided by 1.8 times 10 to the negative 5. And that would give you 5.6 times 10 to the negative 10. Okay, so that's it for the lecture that talks about weak bases. Now that you've gone through the weak acid part. Okay, that's it.